a bit about one chapter of my PhD thesis, and it's all that I will present is just a simple statistical framework to do some trick that might be useful for most of us that are working with classification problems. So basically, what I'm asking here is like a way to calculate the probability of correct identification. So I will present an example from comparing DNA sequences for similarity, and then I will go to the bird species identity case that is actually the focus of my PhD. My background is in biology. I started with that as a complete biologist, trapping birds in Brazil, but then I started to get more complicated problems, like we wanted to sample a huge area and sample community level, and using mist nets, for instance, it's impossible to take guys like that. Then I started to explore audio data sets. Then, still like a biologist, I accumulated lots of data. So I have my database from audio from Amazon. I have 12,000 hours of recordings, which I was able to process only 400 hours of that. But we got lots of stuff. We got more than 40,000 detections of more than 200 species. But as you can see, it's something that you cannot do manually. And then I started to explore like how to take advantage of automation methods, and end up doing my PhD in Finland. This example we have here, it's more or less similar with the example we have in genetics. Those next generation sequencers, they caused some years ago the same revolution as we see nowadays with bioacoustics. Nowadays you can have lots of parallel sequencing of environmental sequences, and then you can generate suddenly lots of data. But once you have lots of data in hand, you need very good bioinformatics methods to handle this data. We have exactly the same problem with bioacoustic. We have many data, and just now we are catching up with ways of automating to properly identify the species and use that data. So in this talk, I'll give a small overview. I will talk a bit about the reliability of automated identification and how that's important. I will explain what are the probabilistic classification methods we are developing. I will explain later how I'm adapting this framework for the audio data, and then I will show some results of this probabilistic taxonomic classification for the bird vocalizations. So I'll start playing a game here. Like, let's suppose that we have an environmental sample that we collected, and then we have sequenced this sample, and we want to run this sample against a search engine, a search database, to find the best match that we have. This is basically what we do with sounds when we have a classification problem. Like you have a sample from the field that you don't know, the species, and you want to classify, you want to find the best match possible. But here we are going to do this trick. I'm getting a sequence that actually I know the species. So it's this Firmitopsis cayenderi, and we are going to do a blast search for the ETS sequence to see which the database answers as the best hit. So as you can see here, the database, the best hit actually is wrong. It's correct only to the level of order. And we have like, it's the best score, it has the maximum similarity, but actually it's not the right species. So let's try to go for a specific database. So I know this sequence that I have, it's a fungal species. So I will go to search in a fungal specific database. So here we have the same problem. The best hit is correct only to the genus, but it's not the right species that we want. But the problem is not getting it right or wrong itself. The problem actually is that you don't have a probability statement about this best hit. And that's the thing. When you don't know, we have an environmental sequence that you don't know the name of the species, how certain are you about this best hit? Like how good is this best hit? So when doing a search like that, what you want is actually to estimate the probability of placement to a taxon, both for the sequence data and also for this acoustic data that we handle. So in 2010 we came up with this paper. handling this question, like what's the probability that the search engine is giving the right answer for the sequence data. And the framework basically is this. You have an environmental sequence that you don't know the name, the origin, and you have a reference sequence and a taxonomy structure of the species, all the species within the reference. This is basically the search system that you have. And with this search system and the query sequence, using this framework that I will explain following, you can get the identifications and the probabilities of correct identification. So before explaining how this works, I want to emphasize that it's actually the same problem that we have in the field. So we have an audio sample that we don't know the species. We want to use some algorithm, some classifier to find the best hit possible, but not only finding the best hit, I want to estimate what's the probability of this search being correct. So it's exactly the framework that I just had for the sequence data. So we have environmental audio files that I don't know the origin. I have a sound library, and I have a taxonomy or a relation tree between the species within my library, and I want to classify and to get identifications and how right or how certain I am about this identification. And how does this work? It's basically a question of which branch I should use. So assume that we have this structure in our reference database. So assume that we are in a family here, and within this family we have several genus, and within the genus we have different species, and within each species we have different reference sounds. And assume as well that we have this genus, but also our sample can be from a species that actually we don't know. It's not inside the database. And for this environmental sample, and you want to be able to compare with all the species that you have in your database and come up with some summary statistics of it. You can have like, let's say, minimum and maximum similarity between your target, your sample, and each of these groups. So you have this, and you want that actually the decision, the classifier, goes for the branch that has higher probability. But those numbers, they are not that intuitive. Like, it's not easy. Oh, it's here, of course, the maximum similarity, but it's not that intuitive for you to know just by looking that that's the right path. So wouldn't it be better to have actually probabilities? Then you can really know, okay, here it's clearly the branch that I want to follow. And I want to emphasize that this is very important to calculate. Because once your reference database is not that good, it's most probably a case that actually the species will not be in your reference database. And you don't want actually to match your best hit with something that it's not what you want. You want to, in this case, you want to have your best hit actually pointing to this option. But where does these probabilities come from? So the framework basically, first we train the model taking advantage of this structure that I explained and the reference sequence. And then we feed a multinomial logistic regression for this model. So a bit more in detail how the framework works. We have two phases. We have a training phase here on the left, and we have a classification phase here on the right. So in the training phase, basically what we take is we feed the models with the taxonomy and the reference sounds that I have, and some covariates that I can plug also. And then I generate training data for each branch of that tree that I showed to you. And after training the model, after generating the data, I train the model and I get the parameter estimation for that data set that I have, for that reference database that I have. Then it's time to start classifying sounds. So we clean the pipeline and we again feed our classifier with the reference sounds, with the environmental sound that I want to identify, and the parameters of the model. Also, we can still plug in covariates if it's interesting for us, and then we can predict the species labels and the probabilities of correct identifications. So this is the paper explaining better. It's in preparation, so you can find this paper soon. And we implemented this using the training phase. It's in Perl, and the classification phase. It's based in R currently, but we are going to have this in just one pack, let's say, soon. But I want to, now that I explained a bit how general it is, I want to show you what we are comparing for the bird case, actually. So instead of using DNA sequences, we are using audio features. And that's the part that is interesting, because when comparing sequence, we are transforming the sequence similarity in probabilities. But here in the acoustic data comparison, the model can be fed with anything that you want. So, for instance, if you are using Sound ID and you want to do feed here with LPC coefficients, you can. If you want feed here straight away with the dissimilarities indexes, you can, with geometric distance, cosine, whatever you want. So it's pretty flexible framework. So the example I will show, I will keep it really simple. So let's take one sonogram and let's collect some parameters of this sound. So I will collect only 15 parameters actually. I will collect 13 cepstral MFCCs, and also the frequency width, and also the vocalization length. And with just 15 parameters, I will fit this model and show you some results. So I collected the database. Basically, it's a database with 440 samples of 77 different sound types from 50 species that I have in Amazon. If you divide this number by this, you are going to see that actually I have very few replicates. It's 6 or 7 more or less. But even those, they can still discerning a bit the species. So here I have also Euclidean distance, because I want to show the most basic distance, but of course you can improve on the distance and have a distance that can discern better the species. What you see in this plot is basically that 440 feature database. So I have 440 feature vectors with these 15 features, and I'm calculating the distance. So you can see for some species we do a pretty good job in splitting. Like the red dots are the sounds within the species, and the blue dots are the sounds outside the species. But we have some species that it's not doing a quite nice job. But let's see how this is going to behave within our model. So as I said, let's run ProTax for this database. I need 3 ingredients to run this model. I need the taxonomy, I need my database, my library, my reference sounds, and I need also, of course, the environmental data to be identified. So the taxonomy here, to keep it simple, I did like this way. Based on the center frequency and the width of my reference database, I did a simple hierarchical cluster just to get different classes. So if you remember that branch structure that I showed you, here I have only 2 levels. I have the color level, let's say, which are 8 colors, and within each color level I have a group of species, as you can see here. And this is the taxonomy I am using to learn. I have the 440 reference sounds, from which I took out one sample to be the test data, and the other samples I trained the model. But they are not samples from the same origin. So I'm using like independent data to verify, to validate this model. And then I ran ProTax for it. So here are the results. Before bombing you with a terrible table, I'll just explain what you're going to see. So basically, we have the name of the sample, the ID of the sample. We have the prediction of our model. We have the probability of the identification being correct. And here is my validation, if it was actually correct or not. So this framework is very interesting, because you can extract 3 aspects that we are interested in. We can extract the best hit, but not only that, we can extract actually all the hits against your database, and those hits will sum up to 1. That's what you want with probability. But more than that, you can estimate 2 more parameters that are very useful. The probability of your sample not being inside the database, and also the probability of mislabeling. So with this framework, you can also correct your database. So I'll show you the complete set of results for that 440 for that 77 sound types that I had. So you can split, for instance, very good identifications, things that I trust. So you can see that the model is getting all them right. So the prediction is correct with the original sound. And we have from a big range of probabilities, from things that the model is pretty certain. Those are the things that I have best references, I have more references, or I have easy situations to compare. And I have, well, here in green I have only the good part of my database. But I also have more information. I still having hits that the model got it right, but with not that high probability. So those group might be something that you want to review manually. So I can say that, okay, this I trust, I will not review. But this I don't trust so much, I will review. And the red lines I will definitely review because I don't trust at all. Because still getting it right, but the probability of correct identification is getting low. So you definitely want to look to these results. And also, I don't want to hide, I also have some bad results here, and I want to talk about these. Like, those are the ones that my model got wrong. And some it got wrong just because I have a very, very low probability of getting it correct. And it's the case where I have very few references, and actually my references are crap. But this cannot happen actually. Miss an error with high probability. This is happening here in this database because, as I told you, I have just like 6 samples per sound type that I have. So it's very, very few. So if I improve this a bit, then I start to get a very nice probability surface, let's call it this way, for this data set. So what are the challenges when using this approach? So basically you need to have good quality reference samples. This is something that every method will need. So that is representative of the species and can discern in between the species. And also you need to choose good sound parameters for compare the species and plug into the model. So this is something that you have you need to have some experience, because it's that type of thing. It's rubbish in, rubbish out thing. If you have a very poor classifier, we cannot do a miracle. And the next steps that I'm looking here are to develop an algorithm that's able to keep feeding this reference library, so I keep improving my probability estimates. For instance, those probabilities that I have more than 99% chance of being right, I can say, okay, I will feed the model for them to work as references, and then I improve my prediction power. And also, I would like to incorporate this framework on algorithms that are working on big data sets, because I think this is a very interesting thing. We are doing a translation between an index that it's not that intuitive, something that it's similarity 1 or 0 for maximum similarity, and then you don't know how it scales up, to probability that it's pretty intuitive to everyone. So the final goal is to have something that you can have your environmental sample, train your reference database, and start classifying the data, but not only classifying with good scores, but you can also estimate probabilities for each of the detections. This approach is very good because you can estimate one probability for each of your detections. Doesn't matter if you have 30,000 detections, you can do that if you want. You can specify a threshold and accept only detections above this threshold. It's very useful strategy as well. And probability is also a natural measurement for uncertainty. So I really understand better when you talk to me about probabilities and not about indexes. And as overall, I would say that like current lines of ecological research, they bring together natural history, massive data collection, as we are seeing here in this meeting, and also creative modeling solutions for estimate parameters. I think this tripod, it's very, very important. Bioacoustics, the way like these tools use it to spatial ecology, they will not happen if we don't develop good classifiers and if we improve the state of the art we have now. So it's very nice to have something that they can do the job automatically, but you need to trust on your algorithm. And this approach here, it's one step further to help people to trust in the algorithm. And to finish the framework, assess the reliability of the identifications using probability, which is natural, and it's ready to plug in another level if you want through the analytical pipeline. For instance, you can use those probabilities as priors for state space models that use that have this observation level that you model detection. So actually it's ready to go to more complex analysis. So this was basically what I had to talk, and if you got interested and want to talk more about this method, I'll be glad to talk during the meeting. Thank you. Yes?
One clarification and eventually one question. The clarification is that the probability that you are calculating is the probability of one specific record to belong to one of the classes that you have defined with the taxonomy. Is that correct?
This plus the probability of this being from something outside.
Okay, but is the probability to belong to one of the groups in the taxonomy that you have defined?
Exactly.
Which is not essentially a taxonomy of a species.
Yeah. Sorry, this I get confused sometimes. It's not the first time that this happens.
Then the question is, well, first, the two variables that you are using to define these groups are included among the set of descriptors that
No.
you are...
Yeah, no.
They are not. And then the question is afterwards, how do you actually validate the new record? I mean, how can you say that it is correct, that it belongs to that group?
Yeah, in the case we have here, we have this, you always need to have a validation step for your data, and that's part of the training phase of your model. You first train the model, estimate the parameters, then you run this model for an independent data set that you know the reality behind, and you see, okay, it's behaving well. Then you start the classification phase with new data, and that's the only way.
Then you know that it's correct or it's not correct because you rerun the hierarchy and then you see that goes to that group or not.
Yeah, I know the reality behind, but they are independent data. I'm not using same training data and same test data.
And
validation.
have you performed any kind of sensitivity analysis in terms of the features that you are using? Are those the best? Have you done any work on that?
No, not yet, but I know this is necessary, especially for audio features, because what is ready to go and publish it is the sequence data part. And the part of my PhD is actually really adapting to that. So I've been playing with many different features here. I try to keep it really simple, but because you can try to improve on two fronts mainly. The raw features, have the right ones, or the distance measure that you have. Better if you can have good for both. And I've been playing around with many different things. So now I need to actually stop on something. So I need to do kind of feature selection and also this part of to see how powerful I am to know the quality of these features.
And you are aware that calculating the probability to these groups that you define with the hierarchical analysis is going to be a lot easier than doing it to a real taxonomy.
Yeah, but I'm not using a real taxonomy here. That's the tricky part that I was about to say, that I think this analogy with sequence data is very interesting to get the idea, but also it's a shooting my feet because I say taxonomy so many times that this glues to people's mind. For the bird case, it's a sound taxonomy, so it's a relation tree between sounds. So in this case, I use this hierarchical cluster that is basically grouping species according to the center and the width of the frequency of the sounds.
Okay, the training, you mentioned training quite often, but you didn't say how long it took. Let's take the data set that you had on the board. How long did that take to train?
For this 440 was very small, like so 3 hours maybe that, because the scripts are already built, so actually just plug. So it was maybe 3 hours to do this, not even that. Because what it does, I didn't explain properly what is training. Yeah. Training means I fit a model to every branch of that tree that I have, a multinomial logistic model. And then I had this on all the hierarchical levels, and then I started doing also kind of leave one out strategy. So I take out one sample from the database that I know, which is the sample, and I feed the model for this database. And then I put it there and take away the next one and feed again the models and so on, so on, so on. So it's actually a very long process, but because it's already, the scripts are built, this kind of goes fast. So maybe 3 hours was the time. But again, it's not that big database. As you start to go wild, then it's more.
What about 30,000? You talked about 30,000.
Yeah, I never tried, but let's see how it scales.
What would the modeling, would it go up linearly or
Okay,
worse?
I don't know this detail. I cannot say to you. I think it's near
linear?
this thing because it's a logistic model, so actually it's linear. I had something to say about the quantity of data. Oh yeah, this training, once you have the data set, this training phase happens only once. So it will take a while, but happens only once. And so let's say for my case, I have the data set Amazon for my field spot, which is like 300 species. It's a lot. It will take a while to run, but I will do this once. And then the classification part, it runs fast because it's other part.
No, go ahead.
Okay, I got 2 stupid questions because I missed something in your talk.
Those are the dangerous ones.
First, what is your audio input? What is this? Is an integer file or you cut in, you sequence it in different?
Yeah. Sorry, these are cut files already, so I'm not taking from the raw data.
So you compute your MFCC and different features on it.
Yeah.
And what is your classifying? This short time windows or the accumulation of?
Yeah, I can do both. For this that I showed here is just the overall sound. But I also worked with framed data.
So you average the priority over the, okay.
That's the thing here.
And if I understand your approach, if I understand well, you are, in order to avoid the large multi-class classification problem, you train a kind of taxonomy in order to reduce the number of visited class in your prediction.
So exactly.
Am I correct?
Yes.
Okay.
You have something?
Yes, you said that the training happens only once, but I thought that the purpose of your framework was to discover new species and add them to the data set. And
Yeah,
new species are discovered in Brazil every year.
But yes. Yeah. But what I meant that you train the data only once is if you are not changing your library. In this case that I showed that the automation part here, this goal that I have to keep feeding, then it's different story. I will need to retrain. Every time that I feed with something new, I need to retrain the system.
Which is surprising that your 2 features you are building your taxonomy is enough to finally to classify more or less correctly all the your training sets. Or your testing sets. So, you have an explanation for this?
Yeah, I think this, I have a very good reference set, which is not, the reality is not like that. So, it's basically, there's no background sounds, it's very, very good reference. And I'm doing, and I didn't mention this, I'm doing some pre-processing on this audio, so it's not completely raw audio. So I'm subtracting background noise, for instance, and I am emphasizing parts that I want. But I played with completely raw data, and of course I get worst prediction. But this also it's an honest game because you can see what's happening. I just get less reliability over my prediction. So those very good predictions, all 0.99, 0.99, 0.99, they drop a bit.
And,
but it's not like, it's still good.
I've got just one technical point. I don't know how many spaces you are in your training set. I get a huge number one. In average, what is the number of leaf you have for each species? Because it's nothing else than the reduction of your multi-class problem. You manage to end up with your taxonomy approaches.
For this case here, I have a few leaves. I think it was 8 per branch. Let's call it this way.
So versus how many species in the original? More than 1,000.
That vocalize that we get with recorders, it's somewhere between 200 and 300 species.
Okay. So 8 versus divided by 200. this is your prediction thanks to your train text input.
Yeah. So.
Well, maybe we shall move.
Thank you.